Hello students and welcome to the lecture. So students, as we know that in the previous lecture we had started our discussion over the upthrust in fluids. Okay, in this basically we had started the discussion over the overview of upthrust, what do you mean by the buoyant, in which we discuss that whenever we try to immerse any body in a particular liquid or any liquid, so basically we experience a upward force from that liquid that we often call as the buoyant force, right? That is what we discuss actually. So in this lecture we are going to talk about this in further, like what do you mean by the upthrust, okay, what is the meaning of upthrust in fluid, and that is going to be our part 2. Okay, in the previous one we discussed several facts. In this lecture we are going to talk about the applications of the principle of flotation, flotation of submarines, flotation of iceberg, hydrometer, lactometer, acid battery hydrometer. So these are going to be the point of discussion for us in this particular lecture. In the previous lecture, I hope that you have revised it in the well enough manner. Before you have come for this lecture, as many times I have reminded you, it's for your own benefit. If you are doing this on the regular basis, the thing will be in your favor. If you are not doing this on the regular basis, thing might be against you. Okay. Before starting this lecture, as usual, we have our small disclaimer over here that we are required to understand before we proceed further. Disclaimer is like, the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck, have any concerns or issues, please contact us at SATHEE@iitk.ac.in and we shall remove the images. Now, let's have a talk over the applications of the principle of flotation. Okay, in the previous lecture we had talked about the principle of flotation, in which we discussed the three cases. In case if you haven't revised them, let me remind you. Three cases that we discuss is, first case, when the weight of body is greater than the weight of displaced liquid. In that case, the body will sink inside the liquid because the density of solid is higher than the density of liquid. The second case that we discussed was the case in which the weight of body equals to the weight of displaced liquid. In this, the body will immerse and float inside the liquid. Okay, because the density of solid equals to the density of liquid. In third case that we discussed, the weight of body is lower than the weight of displaced liquid. So basically, partially the body immersed in the liquid and partially it is upside of the liquid. In such a case, the density of solid is lower than the density of liquid. So these three cases we had discussed. Now we are going to talk about the how we applied this, okay, the principle of flotation in applications of the principle of flotation. First, we could say the flotation of iron ship. So ship is hollow and empty space container air, which makes the average density of ship less than that of water. Okay, like if you look at here, you will find out that this portion is actually hollow and empty space which contains the air. So because of this, the average density of ship is become less than of the water in which it is you can say sailing. Therefore, even with a small part of it submerged in water, the weight of water displaced become equal to the total weight of ship and ship floats, like the second case that we had, when the weight of solid equals to the weight of displaced liquid. So because of this, the weight of ship becomes equals to the weight of displaced water or water displaced, and because of this, ship start floating. Got it? A ship has a white line painted on its side that is known as the plimsoll line. So what are the plimsoll line? We have to understand them, then only we could be able to find out why these. So if you look at here, so you will find, if you have ever seen a ship, so you have seen these things. Okay, so these are the lines that always painted by the side of the ship. These are known as the plimsoll line. These lines indicates the safe limit for loading the ship. So we know ships are always used to carry the items or things from one place to another place, right? And these are also the carriers for the humans from one place to another place, not from nowadays but since ancient times. Okay, so whether these are the humans or the loads and objects, always the ship gets some load, right, whenever these kind of things happen. So basically there must be a safe limit up to which the ship could be loaded. Okay, so these plimsoll lines are used in a manner that these indicates a safe limit up to which the ship could be loaded. A ship is not allowed to be further loaded when its plimsoll line starts touching the water level. So we could say, suppose if you look at this, so here you can say these are the plimsoll lines. Okay, this is the topmost line. So when the ship will load, automatically the weight of the ship goes higher, right? So the water level will start increasing up because the ship will got immersed in the water. And when the water level touches the highest line, it is the last point till when the ship could be loaded. If we load the ship beyond this line, what will happen? The ship will sink, because right now the weight of the ship will be much more higher than the weight of the displaced liquid. It also dangerous for a ship to be too lightly loaded. So we could say it is dangerous for the ship too heavily loaded. Why? Because the weight of the ship will become higher than the weight of the displaced liquid. But if the ship too lightly loaded, that could also be dangerous for a ship. In which scenario? That is what we require to understand. Then if the ship is too lightly loaded, its center of gravity will be higher than the center of buoyancy, and it may be blown over on its side by strong winds. So you can say when the ship having the center of gravity higher, okay, than the center of buoyancy, and it's not that get much of immersed inside the water that is required. So when the ship will sail and it will getting a strong winds from the ocean or sea or river sides, whatever you can call. So basically the ship could be blown over or could be tilted and could be sink. Okay, so heavily loaded or too lightly loaded, both the conditions are not good for the ship. Okay, when ship is not loaded with cargo, the bottom of the ship is filled with sand or stones called ballast, so that its center of gravity is lowered and the meta center lies above the center of gravity. Okay, so when we can say when the ship is sailing empty, okay, the ship is not loaded with cargo, which means the weight of the cargo will not be counted as the weight of the ship, or we can say the weight of the ship will be lower in that case. So that's why the ship bottom must be filled with sand or stone called ballast. Okay, so that artificially the load of sand or stone will work as the load of the cargo. Okay, so does the center of gravity of the ship will be lowered and the meta center will lie above the center of gravity, so the stability of the ship will not be hampered. This marks the equilibrium of ship stable, that we called as a stable equilibrium. If you remember, in the previous lecture we had discussed that there are the three types of equilibrium: stable, unstable and neutral. Okay, so for the stable equilibrium we required a meta center lies above the center of gravity. Okay, and for making the ship stable in the equilibrium condition, we requires to load it with cargo, and if cargo is not there, we will load it with stone or sands called ballast, so that the meta center must lie above the center of gravity, and this condition should be fulfilled. Now, after the flotation of iron ship, it's a time to talk about the flotation of a man. So the average density of body with empty lungs is 1.0 GCMs power minus cube, while with lungs filled with air, it is 1 GCMs power minus cube. Okay, so there are the two conditions: 1.07 GCMs power minus cube or 1 GCMs power minus cube. Okay, this is for empty lungs, this is filled lungs with air. Got it? A good swimmer could lie in water, lie a floating object with his lungs filled with air and nose and mouth just above the water surface. You have ever seen a swimmers like these usually immerse inside the water, and they are swimming across the top layer of water but inside the water, not above the water, but their mouth and nose upside the water, right? The weight of water displaced by him is nearly equal to his own weight. Now here you can see, this is the picture. Okay, this is why he can swim with very little effort. It is easier for a man to swim in sea water than in fresh water. Why? Because the density of sea water is higher than the fresh water. So we can say the reason is that due to the presence of minerals, salt, etc., the density of sea water equals to 1.026 GCMs power minus cube is more than the density of fresh or river water, okay, which is nearly about 1 GCMs power minus cube. So that's why in sea water the density is higher, so the person requires a less efforts for swimming in comparison with the fresh water where the density is lower. Okay, therefore with a smaller portion submerged in seawater, the weight of seawater displaced becomes equal to the total weight of the body. Okay, so it is get balanced, and now the swimmer could easily swim in the water. While to displace the same weight of fresh water, a larger portion of a body will have to be submerged in water, so that the weight of body becomes equal to the weight of the displaced liquid. In Dead Sea, the density of water is nearly about 1.16 GCMs power minus cube. Therefore, a man could easily swim with his shoulders all the time above the water. Because of the density of water, the little portion required to be submerged in the seawater, and then the weight of the body becomes equal to the weight of displaced liquid. Now the flotation of submarines. This is the another topic that we require to discuss. So when we talk about the submarines, we could say the submarines, if you have a looked at them, so you will see this picture, right? Submarines are actually the ships that sail not above the water surface but inside the water. Okay, and if we try to tackle down the birth of the submarines, then most probable answer that we get, it's basically from the Second World War. The Germans were first amongst the other countries that described the functioning of submarines, and they described the making of submarines. Okay, then the Russians came, then the Americans came, so many came, but German designers were the first to design anything like that that could sail inside the water. A submarine is actually a fish-shaped watertight boat which could travel under the water. Its engine works on electric batteries or nuclear energy. Okay, like submarine engines required a power to run. So there are the two types of submarine: electric submarines and nuclear submarine. In electric submarines, basically the electric battery is required to generate a power in the engines, whereas in nuclear submarines, basically the nuclear energy is required to generate the power in the engines. Okay, if we talk about the efficiency, so the submarine's efficiency could be calculated by calculating their ability or duration of their ability to remain under the water. So for electric batteries, the duration is lesser than in comparison with the nuclear energy batteries. Okay, the nuclear energy requires less days to come upside and refuel it. For example, we could say if the electric battery submarine could be inside the water for 3 months. Okay, on the same, the nuclear powered submarine could be inside the water for 6 months. Okay, so we could say the efficiency of nuclear powered submarine is higher than the electric battery submarines. The submarines can be made to mean into the water or rise up to the surface of water as and when desired. So we could say submarine is capable to sail below the water, could also be sail above the surface of the water. It is totally depend on the requirement of the time. The reason is that the submarines are provided with flotation or ballast tanks. If a submarine is to main, the ballast tanks are filled with the water so that the average density of submarine becomes greater than the density of seawater and the submarines mains into the water or below the water. And when the submarines to come to the surface of the water, basically the water that is filled inside the tanks of the submarine called as the ballast tanks, the water will be released so that the density of submarines becomes lower than the density of seawater and the submarine will come to the surface. Okay, so remember, when submarine has to marine under the water, so basically the basalt tanks filled with the water, seawater, so that the average density of submarine becomes higher than the density of seawater and submarine will be floating inside the water. When the submarine is to come to the surface, submarine basalt tanks get emptied by discharging the water into sea and submarine now able to come to the surface of the water. Got it? If the submarine is to rise, the water from the basalt tank is forced out into the sea by allowing the compressed air to enter the tank. That is what I have told you. This makes the average density of submarine less than that of seawater so that the weight of water displaced by it becomes greater than the weight of submarine and hence the submarine rise up to the surface of water. Here you can see. Now the basalt tanks water got emptied by letting the air inside. Okay. After the flotation of submarine, now it's time to discuss about the flotation of iceberg. Okay, so when we talk about the ice, the density of ice is less than the density of water. The density of ice is nearly about 0.917 GCMs power minus cube and water is 1 GCMs power minus 8. Therefore, the huge masses of ice which we call as the icebergs, these seem as heavier than the water, but density wise they are not. So that's why they are able to float in water. Okay, because their density is lower than the density of water. If the total volume of an iceberg is V and the volume of the part floating above the surface of water is small v, therefore the volume will be capital V minus small v, that will be a volume of iceberg submerged. Then by principle of flotation, the weight of water displaced by the immersed part of icebergs become total weight of the iceberg, or capital V minus small v into 1 equals to small v into 0.917, small v equals to 1 minus 0.917 into v, or v equals to 0.083 capital V, or small v by capital V equals to 0.083 by 1 equals to 1 by 12 approx. Thus the Iceberg floats in water with 1/12th part of its total volume above the surface of water and 11/12th part below the water surface. So here you can say if you ever seen an iceberg, so you will only see 1/12th part of it above the water surface. Whereas 11/12th part will be inside the water or below the water surface. Similarly, in seawater, density equals to 1.026 GCMs power minus cube. The iceberg will float with 3/28 part of its volume above the seawater and rest 25/28 part submerged in the seawater. Note, when the ice melts into water, it contracts by the volume equal to the volume of ice piece above the water surface while floating on it. Hence, the level of water does not change. Normally, ice floats in water with 10th/10th part of its total volume above the surface of water and 9th/10th part below the water surface. Let's have a talk on hydrometer. What do we mean by this? So hydrometer is actually an instrument used for measuring the relative density of a liquid, heavier or lighter than water, directly and hence to test the purity of liquid. It works on the principle of flotation. The length of hydrometer immersed is inversely proportional to the density of the liquid in which it is placed. So we can say relative density of liquid equals to density of liquid by density of water. Thus, by finding the length L1 for different liquids of known relative density, the tube could be graduated to read directly the relative density of a liquid. Lactometer. It is specially designed hydrometer which is used for measuring the relative density of milk and hence for testing the purity of milk. The relative density of pure milk is 1.03. The addition of water in pure milk decreases its density, which may go up to 1.015 depending upon the proportion of water added. The commercially available lactometer has the markings W, 1, 2, 3 and M as shown in a figure. Here you can see. The uppermost mark W corresponds to the density of pure water while the lowest mark M corresponds to the density of pure milk. The markings 1, 2, 3 correspond to the relative concentration of water in milk by 75 respectively. As the concentration of water in the milk increases, the density of milk decreases and the lactometer sinks deeper to displace the liquid, which is milk, of weight equal to the weight of the lactometer. However, if the milk is skimmed, its density is higher. So a lactometer couldn't detect the purity of milk if the milk is skimmed. Now, acid battery hydrometers. A hydrometer used to check the concentration or the density of sulfuric acid in an acid battery is called the acid battery hydrometer. The density of acid in a fully charged battery varies from 1250 kgs power minus cube to 1300 kgs power minus cube. If the density of acid becomes less than 1120 kgm power minus cube, the battery needs to be charged. On charging the battery, the density of acid increases and it becomes ready for reuse. The density of acid should not fall below 1100 kgm power minus cube, otherwise the battery couldn't be recharged. With this, we have finished this lecture. It is requested to all of you kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.